Hydration.
Hydration, yeah. Hydration. What was the other one you said? HG, the mercury one, yeah. The mercury one and the boron one. The oxymercuration and hydroboration. Quick review of those, real quick. This is Markovnikov or anti-Markovnikov? Anti. The boron's the anti-Markovnikov one, meaning the OH is on less substituted or more substituted? Less. Okay. Basic mechanism of this one. I'm not going to test you on the mechanisms of these, but just for review. Remember that. Let's try it better. There's a concerted transition state where borane kind of forms a 4-center intermediate or transition state, yeah, where now the boron is poking away from the methyl group and away from substitution. And that's why it's anti-Markovnikov, right? So 2 electrons, 2 electrons. You get an intermediate that looks like that. Then through a little bit of a mechanism, which I'm not going to talk about. Yeah, I like to call it magic, and I know some of my colleagues in the department don't like when I say that. But it's not interesting enough to spend the 15 minutes that would take to explain this mechanism. It in reality is a nice mechanism. It's just we don't have time. Okay? So anybody that wants to know this mechanism can ask me, and I'll tell you it. And sometimes I just say it's magic. Not really implying that it's really magic. Okay, and then we have the Markovnikov one. To make an alcohol. And that's using 2 steps. HGOAC2 and was it?
NABH4.
NABH4. This is a different mechanism. It's not a concerted mechanism. It's a stepwise mechanism that's a kind of carbocation based. So in this one, the alkene attacks, kicks off an acetate. You get this intermediate. This acts like a carbocation, acts like a C+ carbocation, meaning that it has carbocation character, and meaning water is going to attack from the most substituted or least substituted side of that thing. Most substituted. That's why it's Markovnikov. All right. We lost a proton in this process too. Okay, and then the kind of magic step here is the NABH4 step, and that's the demercuration step. All right. Cool. Okay, that's another one that it's a great mechanism. If anybody wants me to show that mechanism, I will. It's fun. It's actually a radical mechanism. This is a radical process. If you like radical mechanisms, it's a great example. Okay. And last reaction to review to make alcohols is makes a diol. OSO4, osmium tetroxide. Second step is there's multiple ways to do it. H2S, or I like Na2S. These sulfur-containing compounds break down the osmium complex. Na2S or H2S. The book may mention some other methods, but it's basically it's an S minus. It's a nucleophilic sulfur. Okay. And quick mechanism review. How does this one work? What kind of mechanism? Another concerted one. Concerted one. OSO4 kind of hangs out by the alkene. Dot, 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 dot. Dot, 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 dot. So and that'll guide you towards the electron pushing. We just kind of push in a circle. I'll start from the alkene and push electrons there, there, and then that there. So it's 3 arrows. Okay. Okay, and then you form this thing, and Na2S breaks it down. Okay, Na2S breaks down. Any ideas how Na2S would break it down? Sulfur attacks, and sulfur has an affinity for osmium, so Na2S attacks the osmium, and I just draw it like lone pair attacks the osmium and then breaks off one of these and then does it again. You know, that's the basic idea of the mechanism. Attacks the osmium once, attacks the osmium again, ultimately kicks off osmium. So from your molecule and you're done. That's the dihydroxylation mechanism. All right. Review. You don't need to know the mechanisms. You do need to know these reactions in case you need them on a synthesis problem. So you need to know how to convert an alkene to an alcohol. And there's 3 ways to do it, right? Okay. Cool. All right. That was number 4, preparation of alcohols. I guess those are the old preparation of alcohols methods. Now a couple new ones. Prep. Of ROH by reducing. By reducing carbonyls. So this is a new one, all right? You haven't seen this one. All right. So by reducing carbonyls, so there are a couple new reagents here, and one of these methods is reduction. REDN for me stands for reduction of a ketone or an aldehyde to an alcohol. All right, and this is the method. There's the generic aldehyde. And we're using NaBH4. Methanol is the solvent here. And I put it in parentheses, meaning that it's not crucial that you memorize that. It doesn't hurt to, but methanol being a solvent is just kind of a side note in this reaction. If you forget the methanol on a test, it's not a big deal. But anyway, methanol is the standard solvent we use for this reaction. We usually have a second step H3O. Okay, NaBH4. You just saw NaBH4. Where did you see it? Erased it. The oxymercuration one, right? Oh, oxymercuration mechanism we just erased. That was another use of NaBH4. This is the more standard use of NaBH4. Okay. All right. So, and And basically, this aldehyde has 2 bonds to oxygen, and it's going to reduce it to the alcohol, which has how many bonds to oxygen? 1. Okay, that's pretty easy, right? Go from 2 bonds to oxygen to 1 bond to oxygen. That's a reduction. Okay. Cool. All right. So the mechanism of this reaction is as follows. So NaBH4. What does that look like? And structure of NaBH4. B with how many hydrogens? 4. Charge of nitrogen, boron? Negative? And you have Na plus. Okay, so this is NaBH4. Mechanistically, we call this H dot dot minus. H dot dot minus. That helps us in the mechanism. If we make this assumption, we call it H dot dot minus, we say it's nucleophilic. It's H dot dot minus nucleophilic. What's a nucleophile do? Attack electrophiles, or electrophilic carbons, right? So, the way I do this mechanism now is I put, in quotes, H dot dot minus underneath, and who's it going to attack? The carbon. The carbon. What's the partial charge on this carbon? Positive. If you push the electrons up, right? By resonance, right? That carbon is delta positive, definitely. So we can just circle the lone pair and attack. Electrons go up. All right. This is an alkoxide. Alkoxide. And what do you think happens when we expose this to acid? It's protonated. You protonate the alkoxide. You're giving it a proton. You got a pretty strongly basic thing there, and it just grabs a proton. All right, that's done. That's reduction of an aldehyde with NaBH4. Okay. Sorry, 3 seconds. The key to this mechanism is essentially recognizing that this thing is nucleophilic H dot dot minus. It's nucleophilic H dot dot minus. Okay? With that, the mechanism is really straightforward. You just attack, and second step, you get a proton, H3O. All right. Okay. Now for ketone, let's just do cyclohexanone. Generic ketone to its corresponding alcohol. Okay. Generic ketone to its corresponding alcohol. And I could let you guess on the mechanism, and you probably get it right, just in case you're not feeling confident in your guessing. H dot dot minus attacks the same way. So ketones and aldehydes react in a lot of the same ways. H3O. H3O grabs a proton. Yeah?
Do you want us to put brackets?
I really don't care, but why do I put brackets? To imply it's kind of like a reactive intermediate. And yeah, it's not not crucial, but that's what it means. Yeah. Okay. All right. So those are aldehydes, ketones. You can also use acids and esters to do this reaction. Only difference is that you gotta switch to a more reactive hydride. More reactive hydride. And the more reactive hydride, it's called lithium aluminum hydride. LiAlH4. LiAlH4. And for this, we use ether as our solvent, diethyl ether. There's some interesting reasons why we don't use methanol. Basic gist is that methanol would catch on fire like in a heartbeat. This stuff is very, very, very reactive. It's like solid hydrogen, essentially. It's like, kind of like a solid hydrogen. And when it reacts with methanol, it makes gaseous hydrogen, a lot of heat, and a big fire. So, personal experience with that one. Okay, almost blew my house. All right. I'll tell you that story later. All right. So NH3O, and so this one makes an aldehyde. First, you add one H, you get an aldehyde. I'm going to say H minus again. What happens when you have H minus and aldehyde? We just saw this a second ago. It goes down to a alcohol. So this is a double two-step reduction. It goes from acid to aldehyde, aldehyde to alcohol. So
Is it possible to stop it at aldehyde?
great question. Yes and no, and we'll definitely address that issue later. Not easily with acids, but with esters, there's ways to do that. Yeah. Good point though. That would be fun if you could. I don't know, fun. It would be useful synthetically if you could do that. From an acid, it's a little difficult though. Okay. So esters have a trick. All right. So lithium aluminum hydride is also a nucleophilic hydride. So it's also a nucleophilic hydride, right? So it does this nucleophilic hydride business. I'm going to say it's also basic. And that's part of the reason it's so flammable, which we'll get to at some point. Okay, so lithium aluminum hydride. All right, so now this part I am going to just say we're going to do this later. It's a little beyond your level right now. It's not that bad, but I have a chapter on this stuff later. So we'll say details later for that part. Now this part you know though. This part you do know already. What happens? H minus, etc., etc. Okay, so it's the same business as before. Okay? All right. Esters. Let's do esters.